Welcome, this is 48F2. This is video 2. So, in this next section, we start talking about a few aspects of forces that give us insights into things like friction and weight and the like. And then in the next chapter, we start using all these insights to actually do statics and dynamics problems. So this next bit is a little bit broken up, but it's important information to master before we move on. And so the first thing I'd like to talk to you about is mass and inertia. The most common mistake that people make is they get mass and weight mixed up. People will talk about something weighing 5 kilograms, and the kilogram is the unit of mass. People will talk about weighing something when, if they're getting the answer in kilograms, they are actually massing something. People will tend to think about mass as being a force with a direction, when in fact mass is a scalar. It has no direction. The weight caused on the mass by a gravitational field has a direction. If you take a mass into space, it is still mass. If you take a weight into space, because the gravitational field strength decreases if you go into interstellar space, you can get to the stage where there is no weight on an object, but there is, of course, mass still on the object. Some physical phenomena depend upon the mass, and that does not change when you go to interstellar space, and other physical phenomena depend upon the weight, and that does change when you go to interstellar space. So it's really important we get mass and weight sorted out. So, well, here's an idea of what mass is. If I take the force due to gravity, which is the weight, and I plot for that force versus an acceleration due to gravity, what I find is, I need to stop. Pause. Bang. So let's get an insight into bang. So let's get an insight into mass. We can get an insight into mass by plotting a force applied to an object versus the acceleration demonstrated by the object. And what we see is that a little force causes a little acceleration, and a bigger force causes a bigger acceleration, and so on. And we find we get a straight line, and that comes from, the sum of the forces equals ma. It's a linear equation. Let me tidy up here a second. If I have different masses, apply the same set of forces to, say, a smaller mass, I will get a bigger acceleration for each different force. And if I have it applied to a bigger mass, I will get lower accelerations. So what we can say is that F equals ma, well, the sum of the forces equals ma. So an object with more mass has more reluctance to accelerate. More mass means more reluctance to accelerate. Here's a force, and here's the object with most mass, accelerates least. So this is big M, and this is an object with little mass, and it accelerates most. This is little m. So an object with more mass has more reluctance to accelerate, and it's said, this object with more mass is said to have more inertia. That was a term that I think was brought up by Galileo. Inertia is that tendency to not like change. And so we say more mass equals or gives more inertia. Let's talk about mass and weight, the effects of the gravitational field. Weight is a force. Weight's magnitude changes depending upon the gravitational field strength at the location of the mass. If I go 50 million miles into space, my gravitational field will be different, therefore my weight will be different, although my mass will not be different. At the Earth's surface, the gravitational field strength, little g is the gravitational field strength, is 10 newtons per kilogram. And this is something which I just want to bang. This is something that I need to quickly review, and that is often people are told that little g is the acceleration due to gravity, and they're told it's either 9.8 meters per second squared, or if you're like me, you round and you go minus 10 meters per second squared. Minus because you're pointing downwards, etc. In fact, g is better described as the gravitational field strength, and it is 9.8 newtons for every kilogram. And if you're like me, you round it to 10 newtons for every kilogram. And the reason why I say that is because although we say F equals ma, and we say, well, yes, therefore W equals mg. And can you see how it's easy to get the idea that the force is like the weight and the acceleration, well, is going to be g. And the fact of the matter is that this is a vector force is equal to the mass times the vector gravitational field strength. Because in physics 2, we're going to say the force due to an electric field is equal to QE. And yeah, the force due to an electric field is like the force due to gravity. And the Q, which is the charge of a particle, is the equivalent to mass. And the electric field strength is equivalent to the gravitational field strength. Nobody would call that the acceleration due to the electric field. So although you can define g as being the acceleration due to gravity, it's better to recognize it as the gravitational field strength. So we say, after all that writing, we say that the force is equal to mass times g. The force due to gravity equals mass times g, and g in this case is equal to the gravitational field strength. The next thing I'd like to talk to you about is friction force and normal force. By now, I think we have the idea that I have a weight on, let's say, a stationary object. It's not accelerating. Well, it doesn't actually even matter about that, but bang. Let's have a look at the frictional force and the normal force. So here's the weight caused by gravitational field strength on an object which is on a slope. And well, we can turn around and say the force of the block on the slope is equal to the force of the slope on the block, and so we have an equal and opposite force pointing in the opposite direction, of course. It turns out that it's very convenient to break up that reaction force into two components. And so we can talk about the reaction force, the component of the reaction force which is along the slope, and we call that friction. And we can talk about the reaction force, the component of the reaction force which is perpendicular to the slope, and we call that the normal force. In this case, we're using normal, not meaning usual, but meaning perpendicular to. It's the math. I think I'm spelling that right. Perpendicular to. It's the math definition of normal. So we say the normal force is the component of the reaction force that is perpendicular to the surface, and we say the friction force is the component of the reaction force that is in the plane of the surface. Frictional forces always go along the interface between the two objects, the block and the slope in this case, and they tend to act in the direction which opposes the tendency to motion. So on a slope, you could imagine this object wants to slide down the slope, even if it's not moving. And so the frictional force will be up the slope, opposing that tendency to motion. If it is moving down the slope, then clearly the frictional force is moving, is pointing up the slope. Ironically, if I had an applied force that was pushing this block up the slope, the frictional force would be down the slope. So it opposes the tendency to motion. I can actually study frictional forces, and I can actually link them to the physical characteristics of the two objects' interface, the surfaces. So we said the physical nature of a friction force. We can define two kinds of frictional force. If I plot a graph of frictional force versus the applied force, let's imagine that I have a block on a level surface and I have a F applied, and that is causing a frictional force. And I can study how these two relate to each other. What I'd find is when the object is stationary, I could apply a tiny little applied force, and because the object is in equilibrium, I'd create a tiny little frictional force. And if I increased my applied force, I'd increase my frictional force, and if I increased my applied force, I'd increase my frictional force, and these would be linear related to each other, and that is this static friction bit here. The object is not moving, but there's a point at which I actually cause motion, and a very interesting thing happens. What happens is that my frictional force decreases as soon as the motion begins, and then continues with a constant value. So I can go, if I have a bigger applied force, I expect to go faster and faster and faster, and what I see is that the frictional force remains constant. So I can divide this characteristic up into the static friction side and the kinetic friction side. This is a nice conceptual recall bookwork question. So make sure, my advice is make sure that you can recreate this graph as needed. We can talk about static friction side, and we can say static friction is the force of resistance to the motion of a static object, and we say that the force of friction is less than or equal to, it's less than or equal to a constant times the normal force. That's interesting. It's the normal force. And the reason why we talk about the normal force rather than the weight is because it really represents the degree of enmeshment between these two surfaces. If I imagine the bottom of the block and the top of the slope, they enmesh, and the bigger force I have perpendicular to this surface, the more enmeshed they become. Imagine pushing your fingers interspersed together, and the more you push, the more they are enmeshed with each other. We could talk about weight, but that only works for a horizontal interface. When I have a steep interface, it's not the weight that I'm interested in, it's the degree of enmeshment, and so I want the force that's perpendicular to the enmeshment, and we know from the previous slide that this is the normal force. So the force of friction is less than or equal to some constant value times the normal force, and this constant value depends upon the properties of the two materials, if you like, the block's material and the slope's material. And it turns out you can look these things up in engineering handbooks, and they will give you them, and they've measured so many different combinations. You could have wood on glass, wood on steel, wood on copper. You could have copper on steel, PTFE on steel. You could have elm, a kind of wood, on birch, another kind of wood, and somewhere you will find somebody has worked out the coefficient of static friction for those combinations. Notice mu s, let's say, is equal to, and let's rearrange, Ff over Fn, the frictional force over the normal force, and ask yourself, what would the units be? Well, what would the dimensions be? And the dimensions would be no dimensions, newtons divided by newtons, or if you like, the dimensions of force divided by the dimensions of force cancel out. Now, sometimes when there's no dimensions, you still have units. So, for example, in sound, when we talk about the ratio of a plane speed to the speed of sound in air, we talk about a Mach number. That's a unit for a dimensionless object, for a dimensionless quantity. Here we have a dimensionless quantity, and we don't give it units. It's just a numerical value, 0.3. Could go up to above 1 actually, 1.3, 0.1, just a range of values ranging from about 0 to about, I'd say, 1.5. I'd say that there's a span of values there. If I look at the second part, the right-hand side of this graph, I'm on the kinetic friction side. We say the kinetic friction is the force of resistance to the motion of a moving object, and we say the force of friction is equal to mu k times Fn. There's no less than or equal to because this is a constant value. We don't worry about this little bit here where it's falling. And again, the coefficient of friction is well known. They're in engineering handbooks, and you can look them up. And it's dimensionless again. Usually, for a combination, the coefficient of static friction is bigger than the coefficient of kinetic friction by a small amount, and that's reflective of the fact that the maximum value for the static friction force is bigger than the value for the kinetic friction force. There's that little fall away, and that's represented in the difference between these two coefficients of friction. The friction force is along the interface in the direction that opposes any tendency to motion, as we mentioned before. Let's have a look at some of these, some conceptual questions. True or false, a 6 kilogram mass has more inertia than a 9 kilogram mass, and that would be false. No, the mass is the measure of inertia, so the 6 kilogram mass would have less inertia, less tendency to want to keep their state of motion. If they're moving, continue moving. If they're stationary, stay stationary. The 9 kilogram mass would have more. Second question. A 6 kilogram mass will experience a larger acceleration than a 9 kilogram mass when both are subjected to the same constant force. Well, F equals ma. And if I have a constant force and mass is decreased, then for a given force my acceleration must be higher. So a 6 kilogram mass will experience a larger acceleration. Yeah, the smaller the force, the bigger the acceleration. So that would be a true answer on that one. True or false? Little g represents the acceleration due to gravity. Now, some teachers will define little g as the acceleration due to gravity. I just think it's not helping you with physics 2. I prefer to define it as little g is the gravitational field strength. So I would say that for my notes, that answer is false. And then little g has units of newtons per kilogram. And yeah, because I define it as the acceleration, and yes, because I define it as the gravitational field strength, little g has units of newtons per kilogram. Let's look at the next bit. A 2 kilogram block sits on a level table. So my shorthand way is I put the 2 inside the little diagram of the block, It's not got a direction because it's a mass, so it doesn't have an arrow on it. I draw the table as level. There's a mu of static friction, mu s is equal to 0.4. No units for that value. What is the maximum force of friction that can be produced by the system? Well, let's remind ourselves. We have our force due to friction, and we have an applied force, and we get this steadily increasing force due to friction, and then at some point we start moving. So the maximum value for the force of friction is here. It's whatever you get at that maximum point. And what we say, of course, is that FF is less than or equal to mu static times Fn. Okay, so I say, well, at the maximum, FF max, well, is equal to mu s times Fn. Okay, so FF max is equal to 0.4 times Fn. And now I realize, oh, I'm not given Fn anywhere. And if you're not drawing a diagram and you're just scanning the words to find the numbers, then that's a problem. But of course, we visualize. What we recognize is that the weight of this object is 20 newtons because it's a 2 kilogram object. It's on the surface of the Earth. And because it's not accelerating upwards or downwards, the sum of the forces vertically must equal 0. So that means there must be a 20 Newton force upwards, and of course this would be Fn, the normal force. I'd call this Fg, the force due to gravity. There's the force that I'm interested in, and so I would say FF max is equal to 0.4 times 20, and that would be 2 4s are 8 newtons. Now, if you could do that part where you determine the value of the normal force by inspection, that's fine, that's great. But sometimes the normal force is not equal to the weight. If, for example, you're on a slope, the weight is still the weight, but the normal force is not equal to the weight. And so you would have to go through a more formulaic way of working that value out. If you can spot it, great, but don't always assume it's equal to the weight. In this next example, which trace best represents the relationship between the frictional force and the normal force for an object that is moving? So now we're talking about motion. We have an object, it's moving, I have the normal force, and I have the frictional force, and the relationship is FF is equal to mu k times Fn. And now I look at my diagram. Most common mistake is people don't look at the axes. They just think they know them. If they have two things in their mind, they'll just somehow impose them on the graph. So this is FF, which is on the y-axis, and Fn, which is on the x-axis. So if I come back to my writing over here, this is the y-axis, and this is my x-axis, and yeah, this is a linear equation, isn't it? If you like, I can make x0 and y equals 0. I can make x equals 1, and then the Fn equals 1, and then y is equal to mu k, and so on. I can recognize it's linear though, and so I should be able to see that. And also, as Fn increases, FF increases, and so There's the trace that I'm interested in. And so my answer on this one would be trace D. Don't think that physics is just putting numbers into equations. It's not. It's going from graphs to equations, putting numbers in, sometimes conceptual. There's many aspects. Let's look at the next page. Recalling the notes, what was the vertical axis of the friction graph shown? So what was this vertical axis? And well, this is going to be my force due to friction. If you don't know that, there's no way of intuiting it from the graph. It's just, you got to know it. You got to know that this is the force due to friction. You got to know that X is the applied force. You got to know that Y is the static side, and you got to know that Z is the kinetic side. You got to, it's bookwork really. So you got to know those things. Don't always read the textbook, always read the notes. It's very important. So this is going to be the force due to friction. So we'll have the friction force. A block slides across a level table. The force of friction between the block and the table is 6 newtons. FF. What is the new force of friction? If the mass of the block is tripled, the coefficient of kinetic friction is quadrupled. Oh, so this is asking you to be able to do ratios. Sometimes physicists and engineers don't know what the original value is, but they know they doubled something, or they halved something, or they tripled something. And so it's important that we can actually deal with ratios. And it's just basically the layout is the issue. So what I say, well, my basic equation is that FF is equal to mu k times Fn. We know that. And I can say my FF new over my FF old is equal to my FF new over, well, we know the old value is 6. But I also know that my FF is equal to mu k times Fn. So I can say my FF new is equal to mu k new times Fn new, and I can say my old FF is equal to mu k old times Fn old. So I took the ratio of the two FFs, and now I'm taking the ratio of the two mu k times Fn's. And it turns out that I know some of these values. I've got to do one more thing. Well, let's just follow it through. We'll let the question direct us. So it turns out that we have let's pause that. So it turns out that we don't know our new value for mu k. We don't actually even know our old value for mu k. All we know is that the coefficient of friction is quadrupled. That means 4 times bigger. So if it was 1 before, it's now 4. We don't need to know the absolute value, we just need to know the ratio, and it's given to us. We could have put down 2 and 8, we could have put down 3 and 12, we could have put down 6 and 24, but 1 and 4 seems like the simplest pattern. And then we want to do the ratio of the frictional forces and we find, it's not there. We were given the masses. Fair enough. So what we say is, our normal force nu would be m nu g nu, and our normal force old would be m old g old. Remember, our normal force is balanced by our Fg, which equals mg. Now I say, well, F nu over 6 is equal to, we had the 4 and the 1, we got to that bit. And then we said, well, hold on, the mass, if the mass of the block is tripled, so the mass would be 3 times bigger than it used to be. What about the gravitational field strength? It's not mentioned. It's sliding across a level table. There's no information about going to another planet or going to interstellar space. So you've got various choices here. It doesn't change. You could put G over G. That would work, if you're comfortable with it. Or you could put down 10 over 10. And that would also work, because it's not changed. It's just a ratio of 1. But personally, what I tend to do on this is I tend to just put down, it's not changed, so it's 1 at the bottom, and it's not changed, so it's 1 for the new value. And then, of course, we have our arithmetic to do. So we get 4 times 3 is 12. So FF nu over 6 is equal to 12. So FF nu is equal to 12 times 6, which equals 72 newtons. So we know the new value for the friction force, even though we don't know the absolute value for the mass, and even though we don't know the absolute value for the coefficient of friction. We just know the ratios by which they changed. And what enabled us to keep it simple, I think, is we had a layout for it. We put the new over the old, and we just let the thing progress logically. The sad thing is, if you're not yet writing in complete equations, if you're using this space as a jotting pad, and you're just putting down the numbers to keep them, visible so that you can do some mental arithmetic, the most common mistake people who use the surface like that get is that they put down the answer of 12. And they put down the answer of 12 because they didn't bother to write that bit down. And so they didn't see that FF nu over 6 equals 12. They just did a whole bunch of work in their heads, got an answer 12 and said, there's my answer. So I would encourage you to always write down complete equations. That's what we're trying to train you to do. This is part of your training, is we're trying to encourage people to draw diagrams and write down complete equations. So I think layout is very important, and there's a layout that works. You can apply this anytime there's an equation. You can apply this technique. When you see an equation, you can think about it as being the substance for number problems. You can think about it as being the substance for graphical problems. You can think about it being the substance for ratio problems. Those are 3 easy things I can do with any equation. So there we have it.